What does it mean to be an ion? We talked about this in chapter 3, but what does it mean to be an ion? It has a charge, okay? So periodic table of ions is going to be your periodic table that shows the charge of every element, okay? And so we're going to use this a lot in the coming weeks because our new topic is technically chapter 7. Okay, we might not get to all of chapter 7 before our final for this semester, but we're going to get a little bit into chapter 7. So we just did 4. We're going to skip over 5 and 6 for right now and go to 7, which deals with chemical naming. Chemical naming. Okay, that's what we're going to start with. Our topic's going to be naming chemical formulas. So we're going to be able to look at a chemical formula and give the full name for it. So this is a really important skill for us moving forward. Okay, so we're going to look at our periodic table of ions a lot. I want you to just take a look at your periodic table of ions and see if you notice any patterns. What do you notice about the left side versus the right side? What do you notice about some of them in the middle? All of that kind of stuff. Give me some things that you see when you look at this periodic table of ions. The right side elements are all negatively charged. Okay, right side elements all negative charge. I would agree. What type of elements are those? Okay, they do include noble gases. Are they metals or non-metals? Non-metals. So look, to the right of that stair-step line, all of those elements are non-metals, and they all have a negative charge. Okay? Everything to the left of the stair-step are the metals, and they have what type of a charge? A positive charge. Okay, so what's the name for an ion that has a positive charge? A cation. So cations are positive. Cations have a positive charge. And what's the name of the negative charged ones? Anion. What'd you say? Anion. Anion. Good. Okay, these are called anions. Okay, so cations have a positive charge and anions have a negative charge. That's right. They're positive. Okay. So our first category of chemical naming is going to fit into this category called ionic compounds. So we're going to focus first on ionic naming. So you're going to give yourself kind of a heading in your notes because this is going to fit under ionic naming. Okay. And so in ionic naming, this is always going to be between. This is going to be a compound that has a cation and an anion, okay? Or another way you could say it is it's between a metal and a non-metal, okay? So ionic compounds have to have something from the left and something from the right on the periodic table, right? They have to have a cation and they have to have an anion. Okay, so if I give you this example, NaCl and CO2, which one of those would be considered an ionic compound? Which one of those has a metal and a non-metal? Raise your hand if you think you know. When you think you know, raise your hand. Which one of those, only one of them is considered an ionic compound. Only one of them has a metal and a non-metal in it. Raise your hand when you think you know. Okay. All right. Brooklyn, what do you think? Which one of those is my ionic compound? The first one, NaCl, because this has a positive charge and this has a negative charge. If you look at carbon and oxygen, they both sit to the right of that stair step, which means they are both nonmetals. So that would not be considered an ionic compound. Okay, so identifying ionic compounds is the very first thing that we have to do. But we have to know it's between a metal and a nonmetal, okay? Or a cation and an anion. That's the very first part, okay? I want to talk a little bit about our periodic table of ions and how the charge came about. Okay, I want you to look at this real quick, okay? I want to see a couple things here. Okay, I know this periodic table is blurry, but you know what it says, okay? So I want you to remind me, how many valence electrons does group 1 have? Group 1 has 1 valence electron. 1 valence electron. You don't have to write this on your periodic table. Don't do that. How many valence electrons does group 2 have? 2. We come over here. It has 3, 4, 5, 6, 7, and 8. Okay, those are the number of valence electrons we have. Now tell me, how many electrons does it take to make an atom happy, to be complete, right? It wants how many? 8. It wants its s and its p orbitals full. That's what we consider a full outer shell. And now that we know what s and p orbitals are, we know that we need to have 2 plus 6 more gives me 8, right? 2 electrons in the s orbitals plus 6 electrons in the p orbitals gives me a total of 8. That's what every element wants to have. So, in the group 1 elements, if they have 1 valence electron, is it going to be easier for them to gather 7 more so that they have their 8, or is it easier for them to give away 1? Give away 1. So, if that's the case, if I'm sodium and I start with 11 electrons, if I'm neutral and I have 11 electrons, is it easier for me to give away my 1 valence electron or to gather in 7 more? We said it's easier to give it away. And so if I'm down to now 10 electrons, I always start with 11 protons. If I've given away my electron and I'm left with 10, what's the charge on sodium? Charge equals positive 1. And what's sodium's charge on our table? Positive 1. So that's where the charge comes from. It's not arbitrary. It has to deal with if they want to give away electrons or if they want to take in electrons. Okay, so let's look at fluorine. Neutral fluorine has 9 protons and 9 electrons. Fluorine has how many valence electrons? 7, because it's in group 7. So it has 7 valence electrons. Is it easier for it to give away its 7 or to bring in 1 more? Bring in 1 more. That would put it at 10 electrons and 9 protons. What would the charge for fluorine be then? -1. Right? Do we see how those charges come about? All of the elements in fluorine's group have 7 valence electrons, which means they want to bring in 1 extra, which would give them all a charge of -1. So we see how that works? What about for oxygen? What did it have to do? It's got 6 valence electrons. So is it easier to bring in 2 to make 8 or to give away its 6? Bring in 2. Bring in 2. So oxygen should have a charge of -2. Okay? Yeah, that's a great question. If I have 4 valence electrons, it's the same difficulty level. So that's why you see group 4 elements don't really have a charge listed. Carbon and silicon don't have a charge listed because they can be +4 or -4. Okay, that's a good question. Kind of depends on what element gets bonded with. Yep. Okay? All right, I wanted to kind of show you where the charges come from so that we could look at that. Now I want to show you one last pattern here because this is important and can help us speed up a little bit. Look at the patterns on the periodic table. All of the elements in group 1 have what charge? Positive. And when it just says positive, that means +1, right? They just left off the 1 there. What about the next group? They all have a +2. If we move over here, boron is not listed, but everything else has a +3. The next one is a 4. So we could go plus or -4, depending on what element it is. Then the next group over is nitrogen's group. What is its charge? -3, -2, -1. Do you see that pattern there? Right? Starting with kind of our group 7 and group 1, we go 1s, 2s, 3s, and then our 4 column can kind of go either way. What's the charge on a noble gas? Yeah, why is there no charge for a noble gas? They already have, not it's a gas, they already have all 8. They already have a p6 orbital that's full. So they don't need to give or take electrons. They already have a full, what's called octet, right? They already have all their 8 that they want. So they don't need any more. Okay, are we good with how those charges are formed? They're not just random numbers. They have a reason for why that charge is, okay?
Those noble gases ever like...
They will bond with things, but it's not usually until you get down like lower where they've got more orbital space to spare, but yeah.
So what's the middle?
Okay, so the middle ones, you see what's different about the ones in the middle?
There's 2.
There's 2 options for charges. Those are called transition metals, and they have a little bit more flexibility about if they want to give away 1 or 2 electrons. They can be stable either way. So they have multiple charges. We'll talk about how to deal with those next week. Okay, so today we're gonna look at pretty simple ones, okay? All right, so let's look at ionic naming, okay? Ionic naming. We're going to start with the easiest type. These are called monatomic ions. What do you think monatomic means? What's mono? How many is that? A single atom. So a monatomic ion is just a single atom. And actually, the naming for monatomic ions is just on your periodic table. Okay? So an ion, if it's a cation and it's charged, it just keeps its regular name. There's nothing different about it. Keeps its regular name. But if it's an anion, do you see what's different about their names? Look at the anions here. What's different about their names?
I don't know.
They all end in yep, IDE. Okay, so if I give you oxide, if I tell you I have something that's oxide, that means I'm dealing with O with a -2 charge. But if I'm talking about oxygen, just regular oxygen, that means I'm talking about neutral oxygen. Okay, do you see the difference there? Ide means it has its charge, but its regular name means it doesn't. But here's the problem. With our cations, we can't tell the difference. If I say calcium, I don't know if I'm talking about with charge or without. So you might say it's a calcium ion or whatever it could be. Okay? So naming them on their own are very, very simple. Okay? Let's get into what are, let's combine them now, called binary ionic compounds. How many elements do you think are present in a binary ionic compound? 2, right? The prefix bi means 2. So there are 2 elements present. One of them is a cation, and one of them is an anion. Okay, one of them is a cation, and one of them is an anion. Here's some rules for when we have the combination of cations and anions, okay? Couple rules. The compound as a whole must have a neutral charge. So what does neutral mean? What numerical value goes with neutral? 0, right? It must have a neutral charge, which is a charge of 0. Okay, that means our positive, guys, our positive charges must equal our negative charges, right? That's what it means to be neutral. So when I put these 2 elements together, I have to arrange them in a ratio that makes sure my positives and my negatives cancel each other out. Okay? So let's look at some examples of these. Let's say that I want to build a formula between magnesium and oxide. Okay? Magnesium and oxide. So if I want to build a formula between magnesium and oxide, I'm going to write out those ions. Magnesium, tell me what charge magnesium has.
2.
Okay? Your periodic table writes it as 2 plus. It makes no difference. I write it as +2. It makes 0 difference. Okay? Oxide has a charge of, yep, -2 or -2. And so, do these fit together perfectly to make a neutral? Yes, they do. And so that means our final formula would be written Mg Oh, that's it. There should be no charges written in our final formula. No charges in final formula. Some people will write it out and then they'll just say, okay, there's my formula, like that, which are no. It has to be written finally with no charges. So here is our correct formula. Okay? Does that seem simple enough?
Yeah.
Okay. What about if we wanted to make a formula between calcium and chloride? Calcium and chloride. Calcium has a charge of +2, and chloride has a charge of -1. So do these fit together perfectly to make a neutral?
No.
They don't. What has to happen?
Yeah, another one.
Take someone's.
Can I change calcium's charge to a +1? I can't. What do I need to do then?
Add another.
I need to add another chloride. Right? So that way they go together in a ratio that makes it neutral. And so that means my final formula would be CaCl2. Right? I need 2 chlorides to balance out that +2 of calcium. Do we agree with that? If it's a -1 and a +2, I'm going to have 2 of them to be able to balance them out. Okay, do you see how that works? Okay, let me give you one more kind of rule here for ionic naming. Not only must the compound have a neutral charge, but we always list the cation first. So it goes cation first, then anion. Okay, we list the cation first, then the anion when we build our formula. And then if I'm going to write out the actual name of this formula, like the formal written name, it's super, super simple. The name of our formula is just calcium chloride. We just name the cation, then we name our anion, and that's it. Calcium chloride. Okay, so the actual written name of it is very, very simple.
But how would, if someone's reading just the written name, how would they know that you have 2 chlorides?
They don't. They would have to build it like we did here. So just by looking at the name, if I say, give me the chemical formula for calcium chloride, you would go, okay, calcium has a +2, chloride has a -1, and so then I see I need another chloride to be able to put it together, and then it would be CaCl2. So just by looking at the name, you don't know how many of each ion there is. You have to build it and make it balanced. Okay? All right, let's try another one. Why don't you give me, let's go from the written name here. So I want the formula for sodium nitride. Sodium nitride. That's the formal name, and I want the chemical formula for it. Okay, so sodium has a charge of +1, and then we need to find nitride. Where's nitride? It is -3. So do they fit together perfectly?
Nah.
They don't. Yeah, go ahead, Nathan.
So would you add 2 more sodium?
That's right. I'm going to add 2 more sodiums so that I get a total of +3 on that side. And that means my final formula is Na3N. Okay, if there's no number here, how many of those do we assume there are? 1. There has got to be 1 of them there. So just like when we did molar mass, if there's nothing listed there, we assume it's a 1. So it gives me 3 sodiums to 1 nitride. So there's our final written formula. Okay, seem good? Okay, let's ramp it up a little bit here. Let's say that I want the formula for aluminum oxide. Aluminum oxide. Aluminum oxide. Aluminum has a charge of what?
+3.
+3. And oxide has a Minus 2. So do these go together nice?
No.
They don't. It's actually going to be kind of complex, aren't we?
We have to add 2 aluminum, 3 oxygen.
Good. Okay, so they said 2 aluminums and 3 oxides. I would agree, right? How did we know we're going to have to go to there? We need to find like basically the least common multiple between those charges, which would be a 6, right? So I've got to get my charges to get to a 6 so that they balance out. And so that leaves me with Al2O3. Do we see how that comes together? If you want to check, listen. If you need to check to make sure your answer is right, you would always just do this. Okay, I know if oxide is minus 2, I have 3 of them. That means I have minus 6. Aluminum is plus 3. I have 2 of them. That means I'm at plus 6. That means I balance, right? You could check over your charges that way. Now, boys, thank you. I'm going to show you how to do it in half the time. Okay, now I'm going to show you how to do it in a method that works quicker, much quicker, okay? So I'm going to start with aluminum, which is plus 3, and oxide, which is minus 2. This is called the crisscross method, okay? And the way it works is this. I am going to ignore the plus and the minus, and I crisscross this charge and crisscross this charge down to a subscript, which leaves me with Al2O3. And isn't that exactly what we did when we did it long ways? Right? Isn't that exactly what we did when we did it long ways?
Does that work for everyone?
It works for every single one. Okay, so this crisscross method works for every single one that we do ionic naming. Okay, we're just going to crisscross them down. Okay? Any questions about what that looks like? We ignore the plus and the minus. We bring down oxygen's charge as aluminum subscript. And we bring down aluminum's charge as oxygen subscript. And we're left with this. Okay? Okay, I want to try another one here. Let's give me the formula for barium sulfide. Barium sulfide. Okay, find barium. It's a plus 2, and sulfide is a minus 2. Now, if I did the crisscross method here, it leaves me with Ba2S2. It's fine, but we have to reduce those down and to just leave it as BAS. If we have 2 subscripts that are reducible by the same number, we need to reduce them down. Because how many of you recognized right off the bat that they're just going to fit together? Right? Then I would have just done that. But sometimes we get so caught up in, oh, I do this crisscross method every single time, we could run into a problem where we forget to reduce that. So we need to reduce our subscripts. Write that down. Reduce subscripts. Reduce subscripts, okay? Sometimes we get so caught up in the crisscross method that we do it, and then it ends up hurting us because we should have noticed right away that they fit together, okay? So you could have just put them together right away, but our final formula should be BAS, not Ba2S2, right? We need to reduce those down. Okay, give me the formula for iridium oxide. Iridium oxide, okay? You try this one on your own. Iridium oxide. All right, so iridium is IR, and it has a plus 4 charge. Oxide is a minus 2. How many of you can see right away what the ratio is? Right? So what should the ratio be? IRO2, right? I need 2 of those. If I did the crisscross method, which is fine, it leaves me with IR2O4. But aren't both of those reducible by 2? So I still have to finish it out IRO2. Right? This is the correct formula, not this. We can't leave it there at our crisscross. We have to reduce. Okay? So either method works. If you can see the ratio right away, by all means, write it out. If you want the crisscross, do it, but then just make sure you might need to reduce at the end. So check that at the end. What? With our chemical formulas, we have to be really careful with handwriting, okay? First of all, some of your handwriting is on another level, but you have to be really, really careful that elements, listen, elements, if they have two letters, the first is an uppercase, the second is a lowercase. So if I am trying to write cobalt, I need to make sure it looks like this. If I'm trying to write carbon and oxygen, it has to look like that. You have to make a distinction between those things. Okay, so this one should not have looked like this, SCP, right? That means sulfur, carbon, phosphorus. That's 3 different elements. If I see a capital letter, that means I think a new element is starting. So make sure you're really diligent about uppercase M's look like uppercase M's, right? They have mountains, not hills, okay? So things like that, we need to make sure that we're being careful because it does make a difference, especially when we're writing out formulas. Okay, so make sure you're diligent with that. Maybe like slow down a minute and make sure your handwriting looks good.